1. Greek fire, the thermodynamic nightmare of the Byzantine Empire. The Byzantine Empire possessed a weapon that defied the natural laws of ancient warfare. It was a liquid that burned continuously on the surface of the ocean, clung tenaciously to the wooden hulls of enemy warships, and violently intensified when doused with water. This was Greek fire, a thermodynamic anomaly and a masterclass in ancient chemical engineering that saved the capital of Constantinople from total annihilation during the massive naval sieges of 678 and 717 AD. Modern science can readily produce modern incendiaries, but the exact chemical synergy, precise distillation methods, and complex mechanical deployment technology of Greek fire remain an unsolved equation in the history of science. To understand this anomaly, we must first break down the chemical paradox. Modern chemical analysis and historical forensics heavily theorize that the primary base of this apocalyptic liquid was naphtha, a highly flammable liquid hydrocarbon mixture distilled from raw crude oil found naturally seeping in the Black Sea region. But raw naphtha does not spontaneously combust upon hitting the ocean, nor does it stick to wet surfaces. To achieve this exothermic nightmare, Byzantine chemists likely introduced calcium oxide, commonly known as quicklime. When quicklime reacts with water, it undergoes a violent, highly exothermic hydration process. The thermal output of this specific chemical reaction is immense, easily reaching temperatures between 150 to 300 degrees Celsius, which is more than enough to hit the flashpoint of crude naphtha. By adding sulfur, the Byzantine engineers lowered the overall ignition threshold and ensured a blinding toxic blue flame. Finally, to solve the problem of fluid adhesion, they dissolved pine resin into the mixture. The resin acted as an organic polymer, a thickener that transformed the thin naphtha into a viscous, tar-like substance. This made the fiery liquid stick to wood, shields, flesh, and bone, functioning exactly like a 7th century equivalent of modern napalm. The only elements known to extinguish it were sand, strong vinegar, and old urine, which starved the chemical reaction of oxygen or chemically neutralized the combustion. However, identifying the potential base ingredients is only a fraction of the puzzle. The true lost technology, and the primary reason modern science cannot perfectly replicate it, lies in the thermodynamics and fluid dynamics of its delivery system. The Byzantines did not simply throw clay pots of this mixture, they projected it across vast distances using heavy bronze siphons mounted on the prows of their fast-moving galleys known as dromons. This required a highly sophisticated, unprecedented understanding of pneumatics and pressurized fluid mechanics. Pumping a highly volatile, friction-sensitive, and spontaneously combustible liquid through a heated bronze tube on a rocking wooden ship, without detonating your own vessel, is a mechanical miracle that baffles modern fluid engineers. Modern attempts to reconstruct the ancient pump design continually run into physical barriers. The siphon system had to draw the thick, highly viscous liquid from a pressurized, heated reservoir beneath the deck, maintain extreme pressure, and expel it through a narrow nozzle to achieve a range of over 30 meters. How did the Byzantines seal the internal valves to hold such pressure? What precise physical mechanism prevented backflash, the lethal phenomenon where the fire travels back down the fuel stream into the pressure tank, obliterating the ship? Some military historians suggest a double-action force pump, originally designed by the ancient Greek engineer Ctesibius of Alexandria, was radically modified for this specific purpose. But creating a hermetic seal capable of handling high-pressure incendiary fluids using only the materials available in late antiquity, such as animal fat, leather gaskets, and bronze casting, is a mechanical feat we cannot accurately reconstruct today. Modern replica attempts either fail to achieve the required pressure or the valves disintegrate under the extreme heat and corrosive nature of the pine resin and crude oil mixture. Furthermore, the formula was fiercely protected by an extreme system of compartmentalization. The Byzantine emperors restricted the knowledge to a select few families and guilds. The mechanical engineers who cast the bronze siphons did not know the chemical formula of the fuel, and the chemists who distilled the naphtha and brewed the liquid did not know how to assemble the pressure pumps. This absolute operational security was so flawlessly executed that when the Byzantine Empire began to fracture and eventually fell, the secret of Greek fire was permanently erased from the earth. Today, while a modern military can easily drop white phosphorus or deploy petroleum-based napalm from a titanium jet, recreating the exact pressurized, self-igniting ancient siphon system safely using only 7th century metallurgy and organic chemistry remains entirely impossible. We know exactly what the weapon did to the fleets of antiquity, but the precise mechanical and chemical blueprint of this ancient superweapon remains forever lost to the dark depths of the Bosporus. 2. Roman concrete, the immortal, self-healing metamaterial. Modern architectural engineering is built upon a fundamental, globally accepted compromise. Reinforced concrete has an expiration date. Portland cement, the foundational building material of the 21st century, is inherently brittle. To give it tensile strength, engineers embed steel rebar within it. However, the moment microscopic fractures form in the concrete, water seeps in, oxidizing the steel. The steel rusts, expands up to 4 times its original volume, and violently shatters the structure from the inside out in a process known as concrete spalling. Consequently, the lifespan of a modern bridge, skyscraper, or seawall is heavily limited, often requiring catastrophic structural maintenance within 50 to 100 years. Yet, across the Mediterranean coastlines, Roman harbors, breakwaters, and piers have been continuously battered by highly corrosive saltwater and intense seismic activity for over 2 millennia. Not only have they not collapsed, but chemical analysis proves they are actually growing stronger as the centuries pass. This is Roman concrete, opus cementitium, a chemical marvel and a dynamic, self-healing metamaterial that modern material science is still struggling to commercially replicate. The foundation of this ancient structural anomaly lies in its highly specific chemical composition. Roman engineers did not use standard gravel and sand. Instead, they utilized pozzolana, a highly reactive volcanic ash sourced primarily from the Campi Flegrei caldera near Naples. When this volcanic ash was combined with quicklime and submerged in seawater, it triggered an extremely complex pozzolanic reaction. While modern concrete simply hydrates and forms a static, rigid lattice that inevitably degrades, the Roman mixture reacted with the ocean water to synthesize rare, highly durable interlacing minerals called aluminum tubermarite and philipsite. The extreme alkalinity of the Roman concrete forced the silica-rich volcanic ash to dissolve, forming a dense, interlocking crystalline matrix that essentially turned the concrete back into solid, impenetrable volcanic rock. However, the true scientific shockwave regarding Roman concrete was only recently unlocked by modern microscopes, revealing a brilliant, autonomous, self-healing mechanism that completely defies modern construction paradigms. For decades, archaeologists and material scientists noticed small, bright white millimeter-scale chunks of calcium scattered throughout ancient Roman ruins. For generations, these limeclasts were dismissed as evidence of sloppy mixing or poor quality raw materials. In reality, modern spectroscopic imaging has revealed that these limeclasts were deliberate, highly engineered micro-reservoirs of reactive calcium. They function essentially as embedded chemical microchips, programmed to repair structural damage. The fluid dynamics of this self-healing process are astonishing. When tectonic stress or physical settling causes a microcrack to form in a Roman structure, the fracture naturally travels through the limeclasts as they have a higher surface area and are slightly more brittle than the surrounding matrix. When seawater or rain inevitably breaches the crack, it strikes the exposed limeclast. This creates a highly localized, calcium-saturated alkaline fluid. As this fluid spreads through the microcrack, it rapidly reacts with the surrounding pozzolanic ash and recrystallizes into calcium carbonate, effectively gluing the fracture shut before it can structurally propagate. The building autonomously bleeds a mineral sealant to stitch its own wounds. So, if we understand the chemical mechanism, why cannot modern civil engineering immediately replace Portland cement with Roman concrete? The barrier to replication lies in thermodynamics, specifically a lost industrial technique known as hot mixing. Modern concrete is made by mixing slaked lime, calcium hydroxide, with water and aggregates at ambient temperatures. Material physicists have determined that the Romans did something terrifyingly different. They mixed raw, highly reactive quicklime, calcium oxide, directly with the volcanic ash and water. This triggered a violent exothermic reaction, driving the internal temperature of the mixture up to 80 degrees Celsius, 176 degrees Fahrenheit. It was precisely this extreme, localized heat curve that allowed the unique limeclasts to form and establish the specific chemical environment required for the self-healing properties to activate. Modern science cannot easily replicate this process on an industrial scale. The thermodynamic variables required to safely control massive, exothermic, hot mixing operations without causing explosive thermal cracking in the concrete itself remain a logistical mystery. Furthermore, Roman concrete possesses incredible compressive durability, but lacks the rapid curing time and immediate load-bearing tensile strength required for modern vertical construction. A modern skyscraper must cure and harden in a matter of days to support the rising floors above it. Roman concrete can take months or even years to fully synthesize its crystalline matrix. Therefore, while modern material scientists can recreate small batches of this self-healing material in heavily controlled laboratory environments, the original Roman blueprint, the exact thermal profiling, the specific granulometry of the ash, and the macro-scale logistical execution that allowed them to pour massive, monolithic, immortal structures remains a lost technological masterpiece that the 21st century cannot economically or structurally replace. 3. Damascus steel, the ancient miracle of metallurgical nanotechnology. For centuries, European crusaders returning from the Middle East whispered terrified accounts of Islamic warriors wielding blades of incomprehensible superiority. According to historical lore, a Damascus steel sword could flex perfectly to 90 degrees without snapping, yet possessed an edge so terrifyingly sharp it could slice through a silk scarf fluttering in midair or cleave a European knight's iron helmet in two without dulling. Visually, these weapons were unmistakable, defined by a mesmerizing, swirling water ripple pattern embedded directly into the metal. For hundreds of years, this material was the absolute apex of blade metallurgy. Today, despite possessing computer-controlled induction furnaces, laser spectrometry, and an atomic-level understanding of metallic crystal lattices, modern materials scientists cannot perfectly replicate a true ancient Damascus steel blade. To understand the absolute metallurgical paradox of Damascus steel, one must understand the eternal compromise of carbon and iron. In standard bladesmithing, adding high amounts of carbon to iron creates an incredibly hard, sharp edge, but the resulting high-carbon steel is highly brittle and prone to shattering upon heavy impact. Conversely, Low-carbon steel is ductile and flexible, capable of absorbing impact, but it cannot hold a sharp edge. Damascus steel mathematically broke this compromise, displaying both extreme hyperhardness and immense ductility simultaneously. The secret behind this impossible duality remained a total mystery until 2006, when a team of crystallographers and physicists at the Technical University of Dresden subjected fragments of a 17th century Damascus blade to high-resolution transmission electron microscopy. What they discovered sent shockwaves through the modern scientific community. The microscopic structure of the blade was permeated with carbon nanotubes and cementite nanowires. Carbon nanotubes are cylindrical nanostructures possessing astonishing tensile strength and thermal conductivity, essentially the holy grail of 21st century material science. Yet, somehow, Middle Eastern blacksmiths operating in the 11th century had successfully weaponized nanotechnology. The origin of this nano-engineering lay thousands of miles away from Damascus in the Indian subcontinent. The raw material for these blades was Wootz steel, a revolutionary crucible steel produced in southern India. Ancient Indian metallurgists would place raw iron, glass, and highly specific organic materials, such as Cassia auriculata leaves, into sealed clay crucibles and fire them in monsoon-driven wind furnaces. As the organic matter burned away in an oxygen-starved environment, the carbon bonded with the iron, raising the carbon content to an extraordinarily high 1.5%. The glass acted as a slag-absorbing flux, purifying the metal. The resulting Wootz ingots were then shipped to Damascus, where master blacksmiths forged them into the legendary blades. So, if modern science knows the exact origin, the crucible method, and the chemical composition, why can we not simply reproduce it? The replication barrier lies in a devastating combination of depleted trace geochemistry and lost thermal mechanical processing. Modern metallurgical forensics revealed that the specific iron ore mined in ancient India was not purely iron. It contained microscopic, highly specific trace impurities of vanadium, molybdenum, chromium, and tungsten. These exact trace elements acted as crucial atomic catalysts. During the heating and cooling cycles, they forced the carbon atoms to segregate into distinct bands, forming the carbon nanotubes and the ultra-hard cementite nanowires, while the softer iron matrix wrapped around them, providing the blade's legendary flexibility. By the mid-18th century, the original Indian ore veins possessing this exact, naturally occurring chemical cocktail ran completely dry. Without the catalytic trace impurities like vanadium, the carbon nanotubes simply refused to form no matter how perfectly the smelting process was executed. Furthermore, the mechanical forging process, the strict thermodynamics of the blacksmithing itself, has been entirely lost to time. Forging hypercarbon steel without shattering it requires an incredibly precise thermal cycling technique. The Damascus blacksmiths had to repeatedly heat the metal to a very specific, relatively low temperature, estimated to be a dull cherry red heat, around 700 to 850 degrees Celsius, before striking it. If the metal was heated even slightly too high, the delicate cementite nanowires would completely dissolve back into the iron matrix, instantly destroying both the microscopic structural integrity and the visible water ripple pattern. If it was heated too little, the hammer blows would fracture the brittle metal into useless shards. Without laser thermometers, these ancient craftsmen judged the perfect thermal threshold purely by the exact shade of the glowing steel in the ambient light of a dark forge. This generational, deeply intuitive kinetic knowledge of heat and hammer velocity died with the master guilds. While modern bladesmiths can produce pattern-welded steel, folding different layers of modern steel together to create a cosmetic mimicry of the water ripple effect. This is merely an aesthetic forgery. the true nano-engineered Damascus steel, born from a perfect storm of lost trace geochemistry and forgotten thermal mechanics, remains an extinct marvel of ancient material science. 4. Vitrum flexile, the Roman pinnacle of polymer chemistry or malleable silicates. During the reign of Emperor Tiberius in the 1st century AD, a Roman craftsman sought an audience to present an invention that threatened to completely upend the economic foundation of the ancient world. According to the historical accounts of Pliny the Elder, Petronius, and Dio Cassius, the artisan handed the emperor a drinking bowl made of a revolutionary material, flexible glass, vitrum flexile. To demonstrate its properties, the craftsman violently threw the transparent vessel onto the solid stone floor. Instead of shattering into dangerous shards, the bowl merely dented, much like a bronze or silver chalice would upon heavy impact. The craftsman then calmly produced a small hammer and beat the dented glass back into its original, perfect shape. Recognizing that an unbreakable, transparent material would instantly devalue the empire's massive reserves of gold and silver, Tiberius asked the artisan if anyone else knew the formula. When the man swore he was the sole inventor, the emperor had him immediately beheaded, burying the greatest chemical anomaly of the Roman Empire in an unmarked grave. From the perspective of modern material science, the very concept of vitrum flexile is a glaring physical paradox. Traditional glass is an amorphous solid primarily composed of a rigid network of silicon dioxide, silica. At the atomic level, the covalent and ionic bonds holding the silica tetrahedrons together are incredibly strong but entirely inflexible. When immense kinetic energy, such as hitting a stone floor, is applied to this lattice, the atoms cannot slide past one another. The bonds simply snap, and the macroscopic structure catastrophically fractures. Metals, on the other hand, possess a sea of delocalized electrons, a fluid atomic structure that allows the atoms to dynamically shift and absorb kinetic shock without breaking their overall bonds. This is why a copper bowl dents and can be hammered out. The Roman craftsman had somehow invented a material that possessed the optical transparency of an amorphous solid, but the structural malleability and kinetic energy absorption of a metallic crystal lattice. Modern attempts to explain or replicate this lost technology continually hit fundamental walls. Today, a form of flexible glass does exist, such as the ultra-thin aluminosilicate glass used in modern foldable smartphones, like Corning's Willow Glass. However, this modern equivalent can only bend because it is manufactured at a microscopic thickness, allowing the material to flex along a highly calculated stress curve. If you drop a modern foldable screen on a rock, it will still shatter or crack. It absolutely cannot be dented and then repaired with a mallet. Modern science also produces bulk metallic glasses, BMGs, alloys that cool rapidly to form an amorphous atomic structure. But these are completely opaque and look exactly like standard metals, not transparent drinking vessels. This absolute lack of a modern equivalent leaves material physicists with two equally mind-bending hypotheses regarding what the doomed craftsman actually created. The first hypothesis suggests that he did not invent a new type of glass, but rather accidentally stumbled into advanced polymer chemistry. Did he manage to synthesize a highly transparent, incredibly pure organic plastic? The Romans were masters of manipulating natural resins, amber, and organic adhesives. However, refining a natural polymer to achieve the perfect optical clarity, thermal stability, and rigid tactile feel of standard Roman glassware, all without the aid of high-pressure petrochemical refineries, is an almost incomprehensible leap in first-century organic chemistry. If vitrum flexile was a bioplastic, it represents a completely lost branch of ancient chemical engineering. the second, and perhaps more terrifying hypothesis for modern crystallographers is that the craftsman actually did manipulate the silicate structure of true glass. This would imply the discovery of a highly specific geochemical additive, an unknown trace mineral or a rare earth oxide that heavily disrupted the rigid silica network when melted. By combining this mysterious dopant with a highly precise thermal annealing process, the artisan may have created a localized metallic glass hybrid. The glass would cool in a state that allowed its molecular chains just enough macroscopic elasticity to deform rather than shatter under sudden kinetic stress. Because Tiberius executed the inventor and likely ordered the destruction of his workshop to protect the Roman fiat economy, we have zero archaeological artifacts to place under an electron microscope. Modern science cannot replicate vitrum flexile because blindly guessing the phase space of every possible silica mineral resin combination is computationally and practically impossible without a starting reference point. Until someone accidentally rediscovers this exact atomic loophole, the secret of hammering glass like hot bronze remains permanently trapped in the 1st century. 5. Iron Pillar of Delhi, the anomaly of passive microcorrosion. Resistance. In the realm of modern material science, iron possesses a fatal, inescapable flaw. It is chemically desperate to return to its natural, oxidized state. When exposed to atmospheric oxygen and moisture, pure iron rapidly decays into iron oxide. It rusts, flakes, and crumbles. This thermodynamic certainty costs the modern global economy billions of dollars annually in corrosion prevention. Yet, standing entirely exposed in the Qutb complex of New Delhi is a massive, 7-meter-tall, 6-ton monolith that mathematically shatters this fundamental rule. For over 1,600 years, the Iron Pillar of Delhi has been mercilessly subjected to scorching Indian summers, torrential monsoon rains, and the howling winds of the Asian subcontinent. By all accepted laws of modern chemistry, it should have disintegrated into a pile of red dust centuries ago. Instead, it stands virtually unblemished, possessing an ultra-thin, invisible shield that completely halts the oxidation process. When modern metallurgists finally subjected the pillar to X-ray diffraction and electron microprobe analysis, they expected to find a primitive equivalent of modern stainless steel, perhaps an accidental alloy containing rust-resistant chromium or nickel. Instead, the results were baffling. The pillar is composed of 98% pure wrought iron. However, the true chemical anomaly lay in what was missing and what was excessively present. The ancient engineers of the Gupta Empire intentionally engineered an iron matrix entirely devoid of sulfur, but heavily saturated with an extraordinarily high concentration of phosphorus, up to 1%, which is significantly higher than any modern commercial iron. In modern blast furnace steel production, phosphorus is heavily purged using limestone fluxes because it creates cold shortness, rendering the metal highly brittle. But the ancient Indian metallurgists harnessed this chemical flaw to trigger an incredibly specific, long-term environmental reaction. When this high phosphorus iron was subjected to the strict, alternating dry and wet humidity cycles of the local Delhi climate, it acted as a chemical catalyst. Instead of forming porous, flaky red iron oxide, standard rust, the surface of the pillar underwent a complex catalytic reaction, synthesizing a microscopic, highly dense, amorphous layer of iron-oxygen hydrogen known as mesowite, delta FeOOH. This passive film is only a few micrometers thick, yet it acts as an impenetrable, self-generating sealant. It completely locks atmospheric oxygen and water molecules away from the underlying iron matrix. The longer the pillar stands in the rain, the more resilient the mesowite barrier becomes. So, if we completely understand the chemical mechanism, Why cannot the modern metallurgical industry simply replicate this pure iron, rust-proof technology? The insurmountable barrier lies in the physical mechanics of its creation, an ancient method known as forge welding, which modern industrial foundries cannot replicate on a massive scale without compromising their own operational parameters. The Delhi pillar was not cast by pouring liquid metal into a giant mold, which is how modern foundries operate. Ancient Indian bloomeries could not reach the extreme temperatures required to completely liquefy iron. Instead, they produced sponge iron, porous, solid lumps of iron mixed with glassy slag. To construct a massive 6-ton pillar, an army of master blacksmiths had to meticulously heat and physically hammer hundreds of these distinct iron lumps together. This brutal, kinetic forging process did not completely expel the slag. Instead, the rhythmic, high-impact hammering physically crushed and distributed the phosphorus-rich slag into a complex, three-dimensional microscopic network woven directly through the iron lattice. It was this exact mechanical distribution of the slag, combined with the specific thermal gradients of a low-temperature, charcoal-fueled bloomery furnace, that provided the perfect microenvironment for the mesoite layer to uniformly form across the entire surface of the monolith. Modern metallurgy is paradoxically too perfect to replicate this. A modern computer-controlled basic oxygen furnace operates at astronomical temperatures, melting the iron entirely into a liquid state and violently purifying it. If a modern engineer attempts to inject 1% phosphorus into a vat of liquid pure iron, the resulting cast metal simply becomes dangerously brittle and structurally useless. Furthermore, modern foundries cannot economically employ thousands of laborers to manually hammer weld 6 tons of semi-solid sponge iron into a perfect cylinder just to capture a specific trace slag distribution network. To recreate the iron pillar of Delhi, we would have to abandon our modern thermal dynamics and intentionally revert to low-temperature smelting, deliberately leaving specific chemical impurities inside the metal and mathematically mapping the physical hammer blows of 1,000 ancient blacksmiths. Ultimately, modern science relies on adding expensive synthetic alloys like chromium to prevent rust. The ancients achieved absolute immortality through the sheer, brute force mastery of pure, imperfect iron, a macroscopic and microscopic synergy that remains an unreplicable ghost of ancient engineering. 6. The Ulfbert swords, a thermodynamic anomaly of the Viking Age. Between the 9th and 11th centuries, the elite warriors of the Viking world wielded a weapon so technologically advanced that it effectively bordered on magic to their enemies. Inscribed with the signature +V LFBERH+T along the fuller, these legendary swords were the absolute apex of medieval close-quarters combat. A genuine Ulfbert sword possessed a supernatural resilience. It could strike a heavy iron shield without vibrating wildly in the user's hand, bend to extreme angles without snapping, and cleave through standard chainmail without dulling its razor-sharp edge. When modern material scientists finally ran these ancient blades through chemical spectroscopy, they uncovered a terrifying chronological paradox. The Ulfbert was forged from crucible steel of such staggering purity and high carbon content that the technology required to create it simply should not have existed in Europe for another 800 years. To understand the sheer impossibility of the Ulfbert, we must look at the grim reality of standard European metallurgy during the Dark Ages. Standard 9th century swords were manufactured using a process called pattern welding. Blacksmiths would take strips of low-carbon iron, heat them in a bloomery furnace, and hammer them together. Because these primitive furnaces could only reach about 1,200 degrees Celsius, 2,192 degrees Fahrenheit, the iron never actually melted. It only became a soft, glowing sponge. As a result, The metal was riddled with microscopic pockets of slag, glassy, non-metallic impurities left over from the raw ore. Every piece of slag was a structural weakness, a fault line waiting to shatter upon the kinetic impact of a heavy battle axe. The Ulfbert, however, contains virtually zero slag. It is flawlessly pure, and its carbon content reaches up to 1.2%, nearly 3 times higher than standard European swords of the era. This perfect distribution of high carbon is what granted the blade its lethal combination of extreme hardness and kinetic flexibility. But achieving this level of purity introduces a massive thermodynamic paradox. To completely remove slag from iron and infuse it uniformly with such high levels of carbon, the metal cannot merely be softened, it must be liquefied. The melting point of iron is approximately 1,538 degrees Celsius, 2,800 degrees Fahrenheit. To create true crucible steel, a blacksmith needs an enclosed environment capable of sustaining temperatures well over 1,650 degrees Celsius, 3,000 degrees Fahrenheit, for extended periods. According to established industrial history, European engineers did not invent furnaces capable of reaching these liquid steel temperatures until the Industrial Revolution, specifically when Benjamin Huntsman developed the modern crucible steel process in the 1740s. So, how did ancient swordsmiths achieve Industrial Revolution-era thermodynamics using only clay, wood, and charcoal? One prominent historical theory suggests that the Vikings did not forge the raw steel themselves but acquired ingots of wootz steel from the Middle East via the Volga trade route. However, even if they imported the raw material, the physical act of heat treating and forging high-carbon crucible steel into a perfect meter-long broadsword using medieval European tools remains an unreplicable mechanical feat. Modern blacksmiths and experimental archaeologists have spent decades trying to reconstruct the exact process. While a modern metallurgist can easily produce flawless, high-carbon steel in a 21st century vacuum induction furnace, no one has been able to perfectly replicate the ancient methodology using only the technology available at the time. If you attempt to heat high-carbon crucible steel in a standard medieval forge, the carbon rapidly oxidizes and escapes into the air, ruining the chemistry. If you strike the metal with a hammer when it is too cold, the dense carbon lattice catastrophically fractures. If you strike it when it is too hot, it shatters like glass. The replication barrier lies in the lost algorithm of the ancient forge. How did these craftsmen accurately control the extreme thermal gradients required to forge weld high-carbon steel without the aid of pyrometers? If they smelted it themselves, what was the exact internal geometry of their crucibles? What precise mixture of organic matter and crushed glass did they use to act as a flux? More importantly, how did they construct a localized forced air draft system using only leather bellows and human labor in the freezing environment of Northern Europe or the deep Eurasian steppes, capable of pushing a charcoal fire past the 1,650 degree Celsius threshold without melting the clay furnace itself? Modern science possesses the final product, but the ancient mechanical blueprint is completely missing. We can cheat by using modern industrial foundries to forge identical weapons, but the actual historical technology, the exact sequence of thermodynamics, pneumatics, and chemical fluxing that birthed the Ulfbert sword in the heart of the Dark Ages, remains a totally unsolved equation in the history of material science. 7. Mithridatium, the holy grail of ancient toxicology. In the annals of pharmacological history, the concept of a single, universal antidote capable of neutralizing any lethal substance is considered a biological impossibility, a myth relegated to fantasy. Yet, in the 1st century BC, King Mithridates VI of Pontus, driven by a severe clinical paranoia of assassination, methodically engineered exactly that. Known as the Poison King, Mithridates dedicated his life to toxicology, reportedly developing a complex biochemical matrix that granted his body absolute immunity to every known poison of the ancient world. This was not merely a historical rumor. His immunity was so absolute that when he was finally cornered by Roman legions and attempted to commit suicide by ingesting a massive dose of lethal poison, his body simply neutralized it. He was forced to order a mercenary to run him through with a sword. The Romans desperately sought to capture his formula, known as Mithridatium, but modern medical science has never been able to perfectly reconstruct it. To understand the science behind this lost pharmacological marvel, we must look at the extreme biological principle of hormesis. Hormesis is a biphasic dose-response phenomenon where a low dose of an otherwise lethal toxin actually stimulates an organism's biological resilience and immune system. Mithridates weaponized this concept on an unprecedented scale. Historical accounts suggest his formula contained up to 65 highly specific, heavily toxic ingredients. He systematically combined neurotoxins from viper venom, hemotoxins, lethal botanical alkaloids extracted from aconite and belladonna, and various heavy metals. By microdosing himself daily with this meticulously calculated cocktail, he forced his hepatic system, specifically the cytochrome P450 enzymes in the liver, and his immune system to continuously generate a broad-spectrum, hyperactive defensive response. However, the true scientific barrier to replicating Mithridatium does not lie in the concept of hormesis. It lies in the impossible biochemical geometry of the mixture itself. Blending 65 chemically antagonistic compounds into a single, stable, ingestible compound is a pharmaceutical nightmare. In organic chemistry, if you indiscriminately mix multiple raw alkaloids, acidic venoms, and metal oxides, the compounds will naturally cross-react. They will either precipitate into useless solid salts, chemically neutralize each other's immunizing properties, or synthesize into an entirely new, exponentially deadlier supertoxin. Mithridates somehow solved this combinatorial explosion. He discovered the exact biological solvents, likely highly specific fractions of aged wine, raw honey, and animal blood, and the precise thermal compounding techniques required to hold this massive chemical matrix in a state of suspended neutralization. The ingredients were ground, fermented, and aged in a way that allowed them to be safely digested without destroying the delicate protein chains of the snake venoms or triggering a lethal overdose from the botanical alkaloids. Modern pharmacology, which relies on the highly controlled isolation of a single active molecule interacting with a single biological receptor, simply does not possess a blueprint for safely reverse engineering a 65-variable, synergistic organic equation without a physical baseline sample to study. Furthermore, even if a modern supercomputer could theoretically map the biochemical interactions of the recipe, the physical reconstruction is permanently blocked by ecological extinction and genetic drift. The ancient world possessed unique botanical profiles that no longer exist today. The most famous example is silphium, a medicinal superplant native to the Cyrene region in North Africa, which was heavily utilized in ancient medicine but was harvested to absolute extinction by the 1st century AD. Without silphium, and with the understanding that surviving plant species have undergone 2,000 years of genetic mutation, altering their chemical and alkaloid profiles, modern scientists cannot source the exact raw materials Mithridates used. The Roman Empire attempted to reverse engineer the formula after conquering Pontus, resulting in a derivative concoction known as theriac. But without the Poison King's exact proprietary knowledge of the catalytic ratios, the original solvent mechanics, and the extinct flora, theriac was merely a shadow of the original. The true Mithridatium, a flawless, universal biological shield born from the paranoia of an ancient king, remains a lost masterpiece of extreme toxicology that modern medicine cannot resurrect. 8. Incan polygonal masonry, the impossible geometry of seismic architecture. High in the Peruvian Andes, sitting on the tectonic fault lines of the Ring of Fire, lie the megalithic ruins of Sacsayhuaman and Machu Picchu. Here, the Inca Empire engineered a structural anomaly that completely defies standard architectural logic. They constructed massive, towering walls using irregular, multi-angled stone blocks, some weighing over 100 tons, that fit together with such terrifying precision that even today, a single sheet of paper or a razor blade cannot be wedged into the joints. They achieved this without a single drop of mortar, without iron tools, without the wheel, and without any known written mathematical system or architectural blueprints. While modern engineers can easily replicate this visual aesthetic using 3D laser scanners and diamond-tipped multi-axis CNC machines, the actual mechanical methodology the Incas used to achieve this perfect three-dimensional spatial geometry remains a complete procedural mystery. To understand the genius of Incan polygonal masonry, one must first understand its ultimate purpose: extreme seismic survival. In a highly active earthquake zone, standard masonry, which relies on uniform rectangular bricks bound rigidly together by chemical mortar, is a death trap. When a severe earthquake strikes, the rigid mortar cracks, the horizontal shear forces shatter the uniform rows, and the wall catastrophically collapses. The Incas mathematically eliminated this vulnerability by abandoning the straight line. Instead of rigid rectangles, they carved massive stones into highly complex, interlocking 3D polygons, some possessing up to 12 different angles. The joints between these stones are not merely flat surfaces. They feature incredibly precise concave and convex curves that lock together like a three-dimensional jigsaw puzzle. When a massive earthquake hits the Andes, an Incan polygonal wall does not resist the kinetic energy, it absorbs and dissipates it. The absence of mortar and the interlocking angles allow the colossal stones to physically dance. They slide and shift slightly, riding the seismic waves, and when the earth stops shaking, the sheer force of gravity and the perfect geometry of the joints force the stones to settle exactly back into their original, perfectly locked positions. It is an autonomous, kinetic shock absorption system engineered out of solid rock. The absolute paradox, and the reason modern science cannot replicate the ancient process, lies in the mechanics of large-scale, three-dimensional data transfer. Shaping a block of andesite or granite using harder diorite pounding stones is physically possible. It simply requires an immense amount of time and brute force. But the true lost technology is the method of spatial mapping. Imagine a massive, asymmetrical, 100-ton boulder sitting on the ground, featuring an entirely random, undulating, multifaceted surface. To make the next block fit perfectly, flush against it, you must exactingly invert the topography of the first stone onto the second. In modern engineering, we would use a laser topography scanner to map the first stone, feed that data into a computer, and have a robotic milling machine carve the negative space into the second stone. How did the Incas achieve this data transfer across three spatial dimensions using only sticks and stones? The most common architectural theory is the scribe and cope method, using a wooden compass to trace the shape of one stone onto another. But this theory immediately falls apart when applied to the megalithic scale of Sacsayhuaman. You cannot simply carve a 100-ton stone, crane it up, press it against the wall to check the fit, realize it is off by 2 millimeters, lower it back down, and sand it again. Trial and error is physically and logistically impossible when the building materials weigh as much as modern passenger jets. The stones had to be carved flawlessly on the very first attempt, with the concave and convex dimensions matching perfectly in the dark, interior space of the joint where the stonemason could not even see. Some modern theorists have become so desperate to explain this mechanical impossibility that they have suggested the Incas possessed a lost, highly acidic plant extract capable of chemically softening solid rock into a moldable clay, a theory thoroughly debunked by geological chemistry, yet one that highlights the immense frustration of modern researchers. The reality is that the Incas possessed a highly advanced, entirely lost system of geometric logic and physical templates. They found a way to perfectly capture the 3D topographic data of a megalith and flawlessly translate that data to an uncarved block without modern surveying equipment. Until modern experimental archaeology can successfully demonstrate how to flawlessly mate two unhewn 50-ton granite polygons without the use of electricity, the geometric mastery of the Inca will remain an impossible anomaly written in stone. 9. Zhang Heng's seismoscope, the mechanical paradox of kinetic filtering. In 132 AD, during the Eastern Han Dynasty, the Chinese polymath Zhang Heng unveiled an invention that essentially functioned as a mechanical sixth sense for the empire. Known as the Hufing Didong Yi, this device was a massive, elaborately cast bronze vessel, nearly 2 meters in diameter. Arranged around the upper exterior of the urn were 8 bronze dragons, each facing a primary cardinal direction and holding a small bronze ball in its jaws. Directly below each dragon sat a bronze toad with its mouth gaping open. When an earthquake occurred, even hundreds of miles away, that was entirely imperceptible to the local populace. The internal mechanism of the vessel would activate. A single dragon would release its ball, which would drop into the corresponding toad's mouth with a loud metallic clang, instantly indicating the precise geographical direction of the seismic epicenter. It was the world's first seismoscope, and its mechanical sensitivity remains an unsolved engineering paradox that modern physicists cannot flawlessly reconstruct. The absolute historical proof of its efficacy occurred in 138 AD, when the device dropped a ball indicating a quake to the northwest of the capital city of Luoyang. Because no one in the capital had felt even the slightest tremor, political rivals accused Zhang Heng of fraud. Several days later, frantic messengers arrived on horseback from the Gansu region, roughly 400 miles to the northwest, reporting that a massive earthquake had devastated their province at the exact moment the bronze ball had fallen. To understand the sheer mechanical impossibility of this feat, one must look at the physics of seismic wave propagation and kinetic noise. Earthquakes generate distinct types of kinetic energy. The fastest are primary waves, P waves, which are longitudinal compression waves that travel deep through the Earth's crust at extreme velocities but cause very little surface movement. These are followed by secondary waves, S waves, and surface waves, which cause the destructive, rolling shaking we physically feel. Zhang Heng's machine was somehow mechanically tuned to detect the microscopic, high-speed, low-frequency vibrations of distant P waves, long before the destructive surface waves ever arrived. However, the true scientific barrier lies in the physics of kinetic filtering. The capital of Luoyang was a bustling, heavily industrialized, ancient metropolis. The ground was constantly bombarded by localized, high-frequency kinetic noise. Heavily armored soldiers marching, massive horse-drawn freight carriages rumbling over cobblestones, and the rhythmic thumping of industrial trip hammers. A standard mechanical pendulum, sensitive enough to detect a microscopic tectonic P wave from 400 miles away, would be so delicately balanced that the mere passing of a heavy cart would constantly trigger false alarms. Yet, The historical record indicates Zhang Hing's device possessed an autonomous physical filter. It completely ignored localized kinetic energy and only reacted to genuine geological fault ruptures. Historical texts describe the internal mechanism as containing a central pillar, which modern mechanical engineers universally interpret as an inverted pendulum. Unlike a standard pendulum that hangs downward and naturally seeks a stable resting point, an inverted pendulum is balanced upright on a precise pivot point, making it inherently unstable and highly sensitive to horizontal acceleration. When a P wave struck, the inverted pendulum would tip, engaging a complex series of internal bronze levers, cams, and cranks. This kinetic transfer would pry open the jaw of exactly one dragon while simultaneously locking the mechanical linkages of the other seven, preventing multiple balls from dropping and confusing the directional reading. Since the late 19th century, seismologists and mechanical engineers across the globe have attempted to build physical replicas of this internal blueprint. While modern engineers can easily construct an inverted pendulum that drops a ball when shaken, no one has been able to perfectly replicate the exact mechanical tuning required to achieve Zhang Heng's legendary combination of extreme seismic sensitivity and absolute stability against false localized noise. The replication barrier comes down to static friction and mass geometry. If the modern replica's central pillar is too heavy, the friction of the surrounding bronze gears and levers simply absorbs the microscopic kinetic energy of a distant P wave, and the pendulum fails to tip. If the pillar is made too light to overcome that friction, it becomes hypersensitive to ambient noise and topples when a door slams nearby. Today, we use highly advanced digital seismographs equipped with electromagnets, lasers, and computer algorithms to mathematically filter out localized kinetic noise and detect P waves. But isolating that exact seismic frequency using absolutely nothing but the physical geometry of solid bronze, gravitational mass, and raw mechanical linkages remains an ancient physical anomaly. The precise friction thresholds, the specific center of gravity, and the brilliant mechanical topology that allowed the Hufeng Didongyi to flawlessly read the tectonic heartbeat of the Earth remain permanently lost to history. 10. Vitrified forts, the unexplained megalithic meltdown of the Iron Age. Across the windswept hills of Scotland and scattered throughout parts of France, Germany, and Ireland lie the ruins of over 200 ancient Iron Age hill forts that harbor an impossible geological anomaly. The stone walls of these sprawling structures are not merely stacked or crumbling, they are fused together. At some point in antiquity, these massive enclosures were subjected to such catastrophic, sustained thermal energy that the solid granite and sandstone actually liquefied, melting and cooling into a solid mass of black and green glass. This physical phenomenon is known as vitrification. While modern science can easily melt rock in a highly controlled, electrically powered industrial crucible, explaining how ancient Celtic or Pictish tribes achieved this massive release of thermodynamic energy in an open-air environment remains one of the greatest unsolved mysteries of experimental archaeology. The core of this mystery is a brutal thermodynamic threshold. To transition natural granite, basalt, or sandstone from a solid state into a liquid, glass-like slag, the material must be continuously subjected to temperatures ranging between 1050 and 1200 degrees Celsius, approximately 1900 to 2200 degrees Fahrenheit. Furthermore, it is not enough to simply flash heat the stone. To achieve the deep structural vitrification seen in these ruins, this extreme thermal envelope had to be maintained for days, if not weeks. This is exactly where standard historical physics collapses. An ordinary open-air wood fire, regardless of how large it is, generally peaks at around 600 to 800 degrees Celsius. The heat simply dissipates rapidly into the atmosphere, A standard lightning strike possesses immense thermal energy, but it occurs in a fraction of a second, causing rocks to shatter violently from rapid thermal shock, not deeply melt and pool into a continuous liquid matrix. Standard Iron Age technology did possess bloomery furnaces capable of melting small amounts of iron, but these were tightly enclosed, heavily insulated clay environments. Scaling the thermal dynamics of a bloomery furnace up to encompass an entire hilltop fortress wall hundreds of meters long is logistically incomprehensible without modern infrastructure. For decades, materials scientists and experimental archaeologists have desperately attempted to replicate the phenomenon to understand how it was executed. In the 1930s, the renowned archaeologist V. Gordon Childe and later teams in the 1980s built replica stone walls laced with massive amounts of internal timber, a design known as a timber-laced rampart. They subsequently set the structures on fire, hypothesizing that as the internal wood burned, it would create an insulated oven effect, eventually causing the surrounding stone to melt. The results were universally disappointing. The burning timber caused the stones to violently crack and the walls to collapse due to rapid kinetic expansion, but the fires completely failed to reach the sustained critical mass required for true vitrification. At best, after packing the ruins with absurd amounts of extra brush and fuel, the researchers achieved microscopic, superficial surface glazing on a few select stones. They produced absolutely nothing resembling the monolithic flowing rivers of glass found at ancient sites like Tapo Nath or Craig Fadrig. Because modern science cannot physically replicate it, we cannot even agree on why it was done. Was it a deliberate construction technique designed to fuse the walls into a single, impenetrable shield? Material physicists point out that this makes zero structural sense. Cooling glass is highly brittle, meaning vitrification actually dramatically weakens a stone wall against kinetic attacks like battering rams. Was it the result of a terrifying unknown incendiary weapon used by an invading army? If so, what chemical accelerant did they use to sustain a 1,200-degree inferno on a damp, rainy Scottish hillside? Some radical thermodynamic theories suggest the ancient builders engineered complex wind-drafting architecture, strategically constructing the walls to funnel the high-altitude valley winds directly into the burning timber cores. This would essentially turn the entire fortress into a colossal, naturally aspirated blast furnace. Other geologists theorize the use of an undiscovered chemical flux, a specific mineral combination heavily mined and applied to the stone to drastically lower its melting point before ignition. Ultimately, we possess no physical blueprint of their methodology. We are left staring at solid rock that was intentionally turned into liquid glass by an ancient people who, according to our modern, rigid understanding of thermodynamics, had absolutely no right to command that level of sheer energy.